Hello students, we are going to study about ideal and non-ideal solution. In last lecture we had studied about Raoult's law. Now we will be studying about ideal and non-ideal solutions. Now we had studied in last class in 11 ideal gases and non-ideal gases. Similarly, here we will study about solution, what are ideal solutions and what are non-ideal solutions. So, ideal solutions are those solutions which obey Raoult's law. Those solutions which obey Raoult's law are ideal solution. Exactly over the entire range of the concentration. Whatever the concentration is there, if they are obeying Raoult's law, that means it is an ideal solution. Raoult's law is obeyed over the entire range of, is followed over the entire range of the concentration. This is very important. Over the entire range of concentration. Now we will see these ideal solutions are formed by mixing two components which are identical in molecular size, which are identical in their structures, and also their force of attraction between the particles should also be of the same range. That means identical intermolecular force of attraction. Intermolecular force of attraction. Component A and component B. For binary solution, when mixed, they must have molecular size similar, they must have structure similar, and also they have force of attraction between their particles of same order, same range. If both the components have these three things of same order, same range, or similarity is there in these three, then we will see the solution formed is ideal one. Am I clear? The two components which are mixed, if their molecular size is similar, if their structure is similar, if the force of attraction between the particle is similar, the solution formed is ideal solution. So we'll see what are the characteristics of ideal solution. As they obey the Raoult's law, is ideal solution obey the Raoult's law. So there must be some properties. See here, del mixing H should be 0. What is H? H is enthalpy. We all know enthalpy is the heat content of the system. So enthalpy, we know it is a state function depending upon the final state and initial state. So enthalpy before the mixing of components, total enthalpy before the mixing of components, and total enthalpy after the mixing of components, that is the formation of solution, should be same. That before dissolution, whatever the value is there for H before dissolution, that should be equal to enthalpy after the dissolution mixing of two components. So we will find in that case del H will be 0. When two components are mixed, enthalpy change should be 0. There should be no change in enthalpy. Enthalpy remains same. H remains same. Value of H remains same. For example, we have taken benzene and toluene. So benzene and toluene, when they are mixed, there should be no change in enthalpy. Neither evolution of heat nor absorption of heat. It should be same, so del H will be 0. Now another case, del mixing V. That means volume change should also be 0. How can be volume change should be 0? We know that liquids either contract or expand. So here if the two components are mixed and they are forming ideal solution, then volume change should be 0. There should be no contraction of liquids and no expansion of liquids. Neither the expansion should take place nor contraction of liquid should take place. So whatever volume, suppose 1 liter of benzene is taken, 1 liter of toluene is taken, total volume is 2. So after mixing also it should be 2 liter. It should not be any change, neither it should be lesser nor it should be more. So del V must be 0. There should be no contraction of liquid, no expansion of liquid. We will find in that case del mixing V will be 0. And such solution where del mixing V is 0 are ideal solution. Third characteristics of ideal solution is what? That molecular interaction, that means intermolecular force of attraction, should be of same order. Third characteristics is what? That molecular interactions that means force of attraction between the particles, whatever was there before in components should be of same order in the before and after mixing of two components should be of same order. That means suppose there is a component AA, whatever force of attraction is there AA and BB, that must be same. First of all, force of attraction between AA particle and force of attraction between BB particle should be of same order. And the new forces formed AB, they should be also of same order. Force of attraction between AA particles, force of attraction BB particles should be of same order. And the new forces which are formed, that is AB, they should be also of same order. So those which follow Raoult's law, they must have molecular interaction before and after mixing of components of same order. Last but not least, they follow Raoult's law. If they follow Raoult's law, then what should be there? PA should be PA naught XA, PB should be PB naught XB, and P should be equals to PA plus PB. That means P equals to PA naught XA plus PB naught XB. These all should be followed. Partial vapor pressure of component A in the solution should be directly proportional to XA. Partial vapor pressure of component B should be directly proportional to XB. Vapor pressure of solution should be sum of vapor pressure, partial vapor pressure of component A and partial vapor pressure of component B. If all these four characteristics are followed, then such solution is ideal. That means there should be no change in enthalpy after mixing of component, there should be no change in volume after mixing of component, no change in force of attraction between the particles, that should be of same range, same order, and they must follow Raoult's law. If these four characteristics are there, then such solutions are ideal solution. Let us see few examples of ideal solution. What are the examples of solution? One example I spoke 2-3 times, that is benzene and toluene. Examples of ideal solution: benzene when mixed with toluene, they are from same homologous series, so they will be having same structure, same molecular size, and also force of attraction between them. If you see benzene, it is like this, and toluene, this is another next homolog of series, so their structure is similar, molecular size will also be comparable, and also force of attraction will be comparable. Another example, N-heptane and N-hexane. If you see hexane 6 carbon and heptane 7 carbon, both are alkane, so their structure similar, molecular size comparable, and also force of attraction will be comparable. Third example, bromoethane and iodoethane. Both are ethane, only change of halogen atom is there, so all the properties will be followed. Chlorobenzene and bromobenzene. Chlorobenzene and bromobenzene. So for ideal solution, we will see that composition in vapor phase will be same to the composition in liquid phase. Whatever the composition of two component is there in vapor phase will be same composition in liquid phase. Whatever mole fraction of component A is in there in vapor phase and component B in vapor phase, same mole fraction of two component will be in their liquid phase. So we will see, if you will see Raoult's law in vapor phase, so we can see according to Raoult's law here, according to Raoult's law of partial pressure, we will see now here we are talking about vapor phase. So according to Raoult's law, the partial vapor pressure of a component is equals to mole fraction is equals to its mole fraction and total pressure. Let's see how. According to Raoult's law, partial pressure of a component, according to Dalton's law, according to Dalton's law, not Raoult's law, according to Dalton's law, the partial pressure of a component is equals to mole fraction to its mole fraction and total pressure. Let's see how. So in vapor phase, Raoult's law will also be little bit different. Let's see how. Let's see how. If you will see that P1, so component 1 A ले लेते हैं, PA equals to YA P, PB equals to YBP. So in general we will see PI for any component, it will be YIP. This is as per Dalton's law that partial pressure of a component is directly proportional to its mole fraction. That means it is the product of equal to product of mole fraction and total pressure. So here YA is the mole fraction of component 1 in vapor phase. YA is the mole fraction of component A in vapor phase. Similarly, YB is the mole fraction of solute, that is component B in vapor phase. So we will see YI, mole fraction of a component, is equals to PI upon P. That means partial pressure of component upon total pressure. This is useful when we are going to do numericals on this basis. Now we'll see about non-ideal solutions. We'll study about non-ideal solutions. Just opposite to ideal solution, we'll see non-ideal solutions have the properties in our next lecture.